Alright, so today I'm going to talk about lessons learned while managing a terabyte scale MySQL database for like what was unknown uptime before. We didn't even have an idea of what was uptime to taking it to 3 nines of uptime, right? So I usually like to start my talks with almost some sort of a empowerment promise, if you were to call it that way, which is what's in it for you, like why should you attend, right? So you're gonna get a good understanding of like what are the challenges of MySQL schema migrations, and we're gonna cover how we solve those. We hopefully you will also learn not just about MySQL and its challenges, but about how to think about database reliability, right, in general. So mostly, let's say you've worked on scaling applications, stateless workloads, etc. The same principles may not directly apply to databases, right, because they're stateful systems. So how do we solve and how do we think about reliability for stateful components? Understand, again, there's a trick that we could use to try to turn stateful components into stateless, and if we could do that well, then we can just use all the existing principles for stateless components to also scale stateful systems, right? We'll see how what I mean by that and soon. And as part of the whole operations work, we have to build simple tools that we can rely on and that will let us sleep well at night, right? And finally, hopefully, you'll get to understand that any workload, whether it's stateful, stateless, etc., you shouldn't treat it as a black box and oh, this is something that the dev team knows. I have no idea what the code it is. So treat more not like a black box, but something that you can peel the layers off, right, and understand. So that's what hopefully you'll get out of this talk. A bit about me. I'm Chinmay. Jaideep is my co-founder. I'm a co-founder at 1-2N. Here is my Twitter, etc. handles. We work with startups and scale-ups on scalability, backend engineering, and site reliability engineering. I have also been writing about some of the work that we are doing in some sort of a story format on Twitter and other media. So take a look at that later. Personally, I love engineering, psychology, percussion, and like Age of Empires. Anyone here? Okay, I see a couple of hands. Okay, others, you should talk to me about Age of Empires later. I'm going to convert you into Age of Empires fan today. Anyway, so the agenda will be again setting some context of what the background of the business is, what was the existing state, how do we solve and get to 3 nines of uptime, right? Existing setup and some challenges like why it was a problem first, and what was the overall journey from sort of unknown uptime to the 3 nines of uptime, and some sort of a summary of what were the lessons that you can take it away and apply it in your own job later. So some context, when I started working with this company, it is a Series A fintech company. Imagine with an engineering team of like 40 people. It was a monolith app with 3 nodes MySQL cluster. The database itself, the storage for the database was 1 terabyte. At peak, we would get 6,000 requests per second for reads on the database, and we would get like about 2K writes per second. Like this was at peak load. I was the first SRE in the team, sort of lead SRE, whatever. Before that, the CTO himself was on call and he had set up all the infrastructure by hand, not much automation, etc. After a few months, like months later, where did we end up, right? So we ended up with a Series B, engineering team of about 150 people. The monolith was also broken down into a couple of more microservices. There were more jobs, more repositories and whatnot. We scaled our database to a 6-node cluster with about 1.5 terabyte data overall. It grew at about on some days like 3 gigabyte per day growth in terms of data size on database, and the peak reads were 20,000 reads per second, 5,000 writes per second at peak. In some cases, on very busy days, it even went into 8,000 writes per second on the database. So imagine the kind of scale that was there. The SRE team was still relatively small compared to what we were managing, so it was a 6 people SRE team. This was the existing setup, right? So let's look at it. There was an application or a bunch of applications. Imagine this to be deployed and run on Kubernetes or any workload, doesn't matter for now. They connected to the database via what is known as a high availability proxy SQL. I'll cover what proxy SQL is. For now, you can think of it like a Nginx for database, right? We had a self-hosted MySQL database. It was MySQL 5.7. There were writes that were sent to primary, and MySQL, the way it works is it replicates via bin log, binary log replication, and you would have replicas. So we had configured read and write separation in some way, right? This was the overall existing setup. What were the challenges with some of this setup, right? Like, so if you worked on MySQL or had to use MySQL in production on large scale, you will know that migrating schema, right, like adding new columns, changing schema, is pain for large tables. It results in some problems which we'll cover later. The overall, from a scale point of view, the transactional versus analytics query separation, what it has to be, it wasn't there in place properly. There was frequent replication lag on replicas, and which would result into database downtime, restarts, stuff like that. There was overall limited observability in terms of we were always reactive and not proactive in a lot of cases because of lack of data or just not having the right metrics in place, etc. Overall, lot of slow queries in the application, which resulted again in more replication lag, more like fueling the fire essentially. And overall, we did not have a good dev prod parity where we could try out things locally or on dev environment and make sure that, okay, the same configuration, the same change would also work on production, right? Because we did not have an exact replica simulation, so we were not confident about that. Overall, like, these were the couple of challenges that we set out to solve. Mainly, you might say, okay, these are all very technical challenges, right? So what was the effect of this? The effect of all of this was reduced product iteration velocity. Like, the dev teams would just not be able to merge PRs which had schema migrations, right? So there were months long PRs waiting for review because they could not be merged because one of the migration requires migrating a table with 100 million rows. Good luck, right? Like, you can't do that without taking the production database down. So almost like some of the important features of the product were grinded to a halt. That was the major sort of problems we set out to solve. So now I'm going to cover the whole journey, right? Like how we were at this stage. How did we go about into sort of good, like 3 nines of uptime, right? So just to put things in context, what 3 nines of uptime really means is it is like about 8.77, close to like 9 hours, less than 9 hours of downtime per year, right? And you can only afford to have like less than 2 minutes of downtime per day, right? That's the level at which we were setting ourselves to. So let's talk about those 7 challenges, right, in MySQL, right? One is this schema migrating large tables, right? Let's sort of understand what is this problem really in the first place, right? So imagine I have a table called ratings. It's a very standard MySQL table where there's a bunch of columns, int, varchar, nothing fancy, and I have 10 million rows on this table, right? If I were to run a migration where I say, okay, alter this table to add a new column called feedback, it's a text column, just add this new column. If I run this directly on master, in one case it took like about 58 seconds, right? So you would press enter after the semicolon and it would wait for 58 seconds before it outputs query okay, right? And it shows you the time that it took 57 seconds here. What does that mean? And what happens on the replica after that, right? On the replica on MySQL, you would have this thing called seconds behind master, which talks about, hey, this replica is now lagging behind master by 56 seconds. What does that mean? That means any writes that have happened in the master in the last less than 56 seconds, they are not replicated yet on the replica, right? That means if I were to make a query on replica, we would not get the records, right? So if we were using, hey, I will use my master only for write query and I'll use replica for read only, you're not going to get the result in the replica, right? That's the problem. And what you see in the status is it is altering the table. Right? So imagine this results in this replication lag. Right? So you can correlate this for 10 million rows. Well, 56 seconds or let's say 1 minute of lag. We had a table with 400 million rows. It would take hours, right? And this is just linearly extrapolating, which we know will not be the case mostly. And we can't afford to do that. We couldn't just run a naive alter table on MySQL. Apart from that, it also results in some other problems, like there is no way to run DML queries on replica during this time. There is this operation on replica is non-possible, means if you run this on master primary node in MySQL and you like, okay, now I'm actually, I'm going to get peak traffic right now, or we have a sudden increase in traffic, let me just pause this migration for some time, we can do this later. Sorry, you can't do that. Like that's a problem, major problem. It's irreversible. Once you've gone ahead, you can't like undo it. Theoretically you can always undo, but practically it has way more challenges. It is non-blocking on primary on your master. That means the writes to the table will still happen in parallel, but the replication lag still becomes a problem. And in our case, because our operations was read heavy, this wasn't like a solution. We couldn't use basic naive alter table. So how do we solve this, right? Like there are a bunch of tools which solve this problem. One of them is called Ghost. It stands for like GitHub's online schema migration tool, right? So OST is like the online schema tool of sorts. It is in a family of tools in MySQL land. One of them is like Facebook's like OSC online schema migration tool. There is another one by Percona, which is PTOSC and stuff like that. I'll not sort of cover the details of all of the differences and whatnot of the tool. We ended up choosing Ghost for some reasons which we'll cover soon. So it's written in Go. It's open source, single binary thanks to being written in Go, and operationally very, very simple to run. You just run the binary and that's it, right? No much state to maintain locally for this tool. It provides really good configuration options to be able to configure how you want to pause replication and all the challenges that we talked about. It has a way to get around those in some ways. And it is used at GitHub scale, where they've migrated like hundreds of millions of row table via all automation, etc. So this is like proven to work at scale, and what we want to do is have tools which let us sleep well at night, right, as SREs. So this is one such tool. How it works? So again, we talked about this challenge, right, where you can't just have a table and migrate it naively, right? So how does Ghost work then? How does it do it? So imagine you have this original table where you have 1, 2, 3, 4, 5 columns, C1 to C5. You want to migrate this table. So you want to add a new column, right? You are going to, let's say, create a table, like a new table now, which is, let's call it shadow table or a ghost table with the latest schema with the migrated column, right? So you have this new column in the new table and you start copying data, right? So you copy the data from your original table to this shadow table. Now you might say, okay, my original table is like 400 million rows, right? So it's not going to copy this data in like 1 hour or a few seconds. It's going to take like forever, maybe 12 hours, 24 hours. So, and during that time, there is more data is being added to my original table. So what happens to that? So if there is new data that is added to the original table, that also gets copied by binary replication in MySQL, right? So it makes sure that the two tables are in sync, and once they are in sync, you also get sort of a status report saying 80% copy complete, 95% complete, etc. Right? So once you have all the data copied, what you do is that is the only time you sort of take a lock in MySQL and you do a swap of sorts, right? You do a variable rename of sorts. So imagine this table structure or schema in MySQL. It was pointing to an original table first. It now points to the shadow table, and you can even delete the original table if you want to. And so that's how, in a nutshell, any schema migration tool, specifically in MySQL, work. What was the usefulness for this, and how does it help us solve that problem, right? So it allows you to do, the Ghost allows you to do throttling based on replication lag. Meaning if my replicas are lagging behind, more than 2 seconds, I can say pause the copy operation, because you don't want to put load on replicas to catch up, like, let them catch up. So pause the operation automatically based on some replication lag, right? That's one, for example, operation. You have a control over the cutover phase, the last phase in last slide, which was changing the table or renaming the table. So you have a good control on when to do that, right? Like you can choose to do this in low traffic time or during night time or whatever. Not that it takes more time to do this, but it allows you to have this control of sorts. I think there's more, but lastly, there is a dynamic change of config without restarts. So I like to think of it as almost like, the patching the tire of a running car, right? You don't have to stop the car. You can just replace the tire, hot swap the tire, and it will still work. So any configuration in Ghost that you want to change, let's say the replication lag or bunch of other parameters, you can do that without having to restart the whole migration or even Ghost process and whatnot. If it crashes because of some out of memory or any problem, it can resume from where it left off, right? So there is some sort of a state management, bookmarking, stuff like that. So that's sort of, this kind of made it much more easy for us to have schema migrations implemented with Ghost. What this resulted in is we were able to migrate this 400 million plus row table with zero downtime. Like that was amazing to see. No downtime for MySQL database, no replication lag beyond what we couldn't control. Like just plain old, good old, simple migration. That was like a massive win. And after that, the whole floodgates opened. We had like 7 database schema migrations per month almost that were implemented using Ghost for tables more than a few million rows. It increased product team's velocity. All the PRs that were waiting for merged, most of them got merged, and then like the product velocity increased. What we also did is we created checklists and runbooks so that anyone in the team could run Ghost. You don't really need to have a very strong database knowledge. For example, we created a very robust checklist and runbook so that any SRE could automate this as well. So recap, we talked about the first major challenge, which is schema migrating large tables. Let's look at the next 3. One, the transactional and analytics query separation, replication lag, and database downtimes, right? How do we solve that, or what did we do to fix these? So again, let's start with the transactional and analytics. So again, this was the original setup. For analytics, we were using Metabase, and the initial configuration was that Metabase would directly connect to MySQL primary. And what would this result in? It would result in a large query taking down production, right? Like you would have a very large group by select over a almost table scan query on primary. Good luck handling that, right? So this was the situation that we faced. Sort of interim solution was to point, first of all, like why are we pointing to primary, right? Like there is no need to point to primary because anyway this is pure analytics queries and we're okay to have much behind the data and whatnot, right? So we said that let's centralize all access control and use proxy SQL. So Metabase points to proxy SQL. Based on those queries, we pinned it to a particular replica. So we almost said, okay, this is a MySQL replica that we will use for all analytics queries, right? That means it will not even handle any production traffic. So you almost separate the OLTP and the OLAP workloads in some way, right? This resulted in like massive improvement to start with. Eventually this wasn't still a good enough use case. So in the long run, we migrated the analytics part to BigQuery. So we set up like a pipeline where MySQL would also get data into BigQuery every few intervals or whatever, and then Metabase would just point to BigQuery in that case. Let's talk more about this proxy SQL concept, right? Like what is it? Like if you have not ever used proxy SQL or any database related tools, you might not know about this. So let's talk a bit more in detail because it's pretty interesting. So proxy SQL is a high performance, high availability, protocol aware proxy. What does protocol aware means? I think we all, being SREs, we understand high performance and high availability, although again those are still buzzwords. But protocol aware means it can use SQL, like it can speak SQL natively, right? So it's written in C++, it's open source again, you can check it out. The best way I can think of proxy SQL for all like who managed applications is it's like Nginx but for database. So think what all Nginx does, right? It allows you to have load balancing. It allows you to have routing across your various application servers. It does a health check for these backend app servers, stuff like that, right? So it's almost like, and it speaks HTTP. So your app, you can directly point your users to Nginx, and then it will speak HTTP for your application server's behalf, right? This is what I call by turning your sort of stateful systems into stateless. So database is a stateful system. You kind of move this state away from the database and move it into proxy SQL. So it's not like getting rid of the state. It's just sort of moving it in a more controllable fashion, right? Separating almost like data and metadata. Think about it that way. And one interesting thing you might have heard is it says all problems in software can be solved by adding another level of indirection, right? So you add proxy SQL as a level of indirection, and it turns your stateful database into stateless ones. So let's talk about again how it works and what it does. So how proxy SQL works, again it uses a state because the state has to go somewhere. It can't the metadata, right? So imagine you have these this is on proxy SQL. You have these MySQL servers, right, where the host group ID, let's say 10, 20 are just two numbers, but this belongs to primary. 10 belongs to primary, 20 belongs to all my replicas. So, and these are the IP and whatnot, right? You can configure weights for traffic distribution in a sense that, hey, send 300 and 300,500. So it's like 3, 10, 5 ratio for your reads, and for all write traffic, it will anyway go to primary. So you can kind of configure the weights to distribute the traffic. You can configure something interesting, which is replication lag, where just like in Nginx we have a health check for applications, and if the app is not responding and the health check fails, you're not going to send traffic to the app, right? The Nginx does that automatically. So similarly, proxy SQL will say, okay, anytime the replication lag goes beyond this value for this node, I'll not send traffic to it, right? It will automatically sort of not send traffic and make sure that the node has time to catch up with the replication lag. There is some other fancy things it can do as well, which is query rewriting and query routing. So imagine this, like there is a table called MySQL query rules, where what you can do is you can configure various rules, priorities and whatnot, and say, this select for update, meaning any update kind of query, point it to my primary. Any just select queries, point it to my replication, my replicas, right? So that it doesn't have any problem of routing the queries in that way. You can apply and not apply these rules at runtime. You can change this configuration at runtime without having to restart proxy SQL, database, any of that, right? So it's super sort of epitome of moving the state where it can be managed efficiently, right? We'll quickly cover some features. So it is application layer proxy in a sense, like similar to Nginx. It speaks HTTP. Proxy SQL speaks SQL, right? So your applications can directly connect to proxy SQL as if they are connecting to database in that way. It allows zero downtime changes. Any configuration change, you can apply it, not apply it, reverse it very easily without any problem. Can act as database firewall in a sense that you can control all your gatekeeping of users, who connects, how many connections from each node and whatnot. All of that can be configured almost like as a gatekeeper, right? And for database. It has these advanced query rules that we talked about. It can also do good support for sharding or even rewriting the queries, dropping some PII columns, for example, stuff like that. We didn't end up using these features, but it has these features. And lastly, like the failure detection, which is a core feature of any load balancer, which is ensure the health check works, and if only send traffic to the healthy nodes, right? So how did proxy SQL help us? Like what it allowed us to do is it allowed us to efficiently separate our read and write traffic. It allowed us to also pin a particular analytics traffic to a particular replica, right? Then we were able to take a DB node down for maintenance. We could just say, hey, proxy SQL, don't send much traffic to this database node, or just don't send any traffic at all. Take the database down for maintenance, patching, upgrades, whatever. Plug it back in, let it catch up from replication lag, and enable the routing again, right? Like very, very easy. So this is again what I mean by removing the state from and making your stateful system stateless in some ways, right? You can roll out any database configuration flags, etc. much more easily. If you want to change some configuration flag and test it out, you can just do it on one of the replicas, see whether it has an improved performance in terms of query or other parameters, and then roll out those changes across all nodes. Health check we already covered. Failure detection is kind of a result of that in some way. So like these proxy SQL by itself like helped us achieve most of these other like 3 points that we covered earlier. Now let's talk about this the limited database observability, slow queries, and like how did we handle the whole dev prod parity, right? Again, coming back to the existing setup, what we had for database in terms of observability earlier was we had a MySQL exporter which was deployed on primary replica, and then it was sending traffic to it was sending its metrics to Prometheus. We would then be able to get those metrics on Grafana. This was our existing observability setup. Some sort of challenges or limitations of sorts with that, not that we couldn't make it work, but the challenges were it was not integrated well with our application observability setup. So we had a different setup for a different Prometheus, different Grafana for applications and other services, and our database was separate. So what we couldn't do is we couldn't correlate things properly with other metrics from application. We couldn't, we had to kind of self-manage and host this stack. Not that it can't be done, but it was proving out to be too much of a challenge for a small SRE team at that point. So in a sense, what we decided was an org-wide decision was made to centralize observability in some way, and we decided to go with a third-party vendor, in this case Datadog, where all of application, infrastructure, database, queues, APMs, all of that logs or metrics and events would funnel into Datadog, right? And we would have sort of centralized plane for all of observability. This was more like a org-wide decision where we said, let's not sort of manage our entire observability stack ourselves, for now at least, until like we have enough capacity and we are okay to spend money right now and give it to a vendor for now. This helped in case of database. We could find top queries, which are slow queries. We could find host metrics with all like MySQL thread counts, InnoDB metrics, active connections, like more details about explain plan and whatnot, much more easier in Datadog, again, thanks to its sort of features. Not that this couldn't be done with Prometheus Grafana setup, but again, the choice was made to make everything centralized in that way. So this kind of helped us solve some of the major challenges with respect to making data available. With respect to dev prod, what we did is, first thing is like creating a staging sort of environment which is similar to prod, with all database nodes configuration trimmed down, but the data size still being available. So we would still have 1.5 terabyte of randomly generated data. There are tools that allow you to create similar like large data sets in MySQL, or I'm sure in any other database. So we use that. To change any configuration flags or whatever, we would do a load test on staging. We would change this configuration flag, run a bunch of queries, simulate a bunch of load, and see how that affects our database, right? Only when we are confident about this, then we would roll out those changes to production as well. All these tools like this helped us in Ghost and Proxy SQL and other tools also. Like we could test all of them on staging without having to worry about downtime on production and failures happening directly on production. Right, so all these were tested before, and then we could roll it out on production. So with this, like we've covered how majority of these challenges were solved. This didn't mean we had no extra unknown issues or problems, right? We had some Heisenbergs, I call it. Like Heisenberg is a bug where you try to study it and it disappears. Like you can't like measure it properly, right? So this was almost like having those potholes on the road. As we walked the journey, we could see these Heisenbergs sort of go down in terms of frequency. So what were some of them, right? Like one was MySQL restart failed. In one case, we were maintaining and running an upgrade on one of the nodes, the restart itself failed. Almost like task failed successfully kind of meme, right? What we had to do was we had to kill the process, restart it. That meant now it would go into the whole transaction, redo logs, read all the previous logs, and it would take like half an hour to get up to date, right? Up and running. There was replication broken on only one of the replica. This meant that we had to now skip that particular record of replication and go forward. Again, we couldn't figure out why this happened, but just happened for one of the nodes. And lastly, I think there was still occasional replication lag due to long running queries and whatnot. So quickly summarizing the tools, for schema migration, we went with Ghost, turned out to be super well. Proxy SQL almost helped us with like coupling the database, decoupling the database and the application, making it stateless in some ways, and bunch of other processes and practices, right? Like creating good runbooks, checklists, making sure there is pairing that happens within the SRE team. We are able to centralize observability, having dev prod parity, having good confidence in the test suites, etc. By this version of sort of the talk that I'm doing right now, I wrote about this as a Twitter thread. In case you are into that stuff, like take a look at that later. As of today, we are not self-managing that database. We have migrated that to a cloud provider. I've written about that too, and maybe this is like in future we can do a talk on how that migration went about, what were the challenges in that, and how did we go about it. That could be a future talk in itself. Yeah, that's it. Connect with me. I'm here on Twitter, LinkedIn, etc. We've been like building some sort of Go bootcamp. At 1-2N, there is SRE bootcamp in pipeline, and I write about these pragmatic stories on Twitter and other media. So check us out, and happy to discuss more war stories with fellow SREs here. Thanks.
Thanks, Chinmay. Again, you are also on time. So I think you have a habit of sticking to the SLAs. Thank you.
Yes.
Again, questions, please.
I'm reliable 99.9% times.
Hi, Chinmay, thank you so much for a very insightful topic. Two questions. One, both are related to the same thing. You talked about that when you are migrating, you basically create a new database or shadow database. And you basically pause it if there are certain critical things or lags happening, right? So was it not that it required a specific time-based migration, that you had all the time in the world in your hand when doing this? That is one. Second is about the storage part, because you have 400 million records in the thing. You had ample storage also available. So there was no constraints from both these points because of which you choose Ghost. Is there any other tool which you would have chosen if these two constraints would not have been there?
Yeah.
Would have been there.
Got it. Good point. I think time. So thankfully we had ample time in our hands, in the sense that without any of these tools, product team was anyway blocked. They couldn't do these migrations before. So they were like, do whatever it takes to make it work. And if it's okay if it takes a day or a week or whatever. So initially we slowly rolled out small tables with 10 million, 25, 50 million, etc. And then largely we did this 400 million, like the largest table. That was the good part about the domain and how we were. In terms of the second question, we had to worry extremely about the database storage, because we had like a 2 terabyte disk attached to as a database node for every node, and we were already at 1.3 or whatever. And we had calculated, okay, this 400 million row table would mean we have to add, like it would basically replicate this data. That means it is like 200 GB. So we're going to already clock 1.5 terabyte, right? And we have 2 terabyte of storage. So that way we had to do some sort of planning. I think eventually later we also increased the disks on the nodes easily. And the one other way we were able to do that was with proxy SQL. Again, you could take the nodes down for maintenance, do whatever you want with them, and then make them back up again. You could also switch master from one master to another master easily with proxy SQL as well. So that is like the feature that we used, where we could, if you wanted to do a maintenance on master, right, because it is still a single node in that way. So that was much more easier to do with this tool. Yeah, hopefully that answers. Yeah, go on.
Hey, so I have a couple of questions again about the schema migrating large table with Ghost. So first, it's basically going to create a temp table and going to do the migration for you, which is faster, and then copy the data into it. Now I might have a bunch of triggers and stored procedures working against this table, and when I do an rename and bring this as the live table, how are these going to start applying to the new tables? That's the first.
I think. Yeah, very very interesting. So this again, thankfully in our case, we did not have any triggers or any stored procedures as such.
Okay.
Ghost does allow some like you'll have to specifically read that documentation part, etc. Like for example, any schema migrations tools, one of the challenges that they have is this foreign key. Like imagine even you have foreign keys of with other tables, during the table rename, that is going to cause a problem. And there are ways in which the Ghost team, or even there is a bunch of tools like Percona's tool and Facebook's tools, they have documented what you can do in that case. Like simplest option is to see if you can drop the foreign key for some time, do the migration, re-enable the foreign key. For that you have to make sure your application is able to not let any random data be written, because then when you add the foreign key constraint, it is going to fail otherwise. So there are those like very interesting caveats with that we'll have to look at. For our case, the two that you talked about thankfully did not apply. Otherwise it would have been again some more nightmare, some more debugging, some more like setting up more type of exact like simulating the exact nodes, etc. would have been the case.
Got it. Yeah, I have another question. So we are migrating 400 million row table with Ghost, and it went from 0 to 400 million from your day one to today. It took that much time to grow to that size.
Yeah.
And now say you're taking 10 hours or whatever to bring that up in a temp table. Wouldn't that also cause replica lags, because your write is at a much faster pace than usual? And how does Ghost handle that?
Yeah, correct. So Ghost, the way it works is it also replicates via binary log. So it almost acts like a replica. Like how MySQL replicas work, it works in the same way.
Okay.
There are other tools like Percona's like online schema tool that works via triggers. So in some ways, like it sets up a trigger on the existing table. Anytime there is a new addition or update or delete, you would get the trigger, and then that gets copied to the other. Okay. One of the problem with triggers is that you can't pause them, right? In our case, thankfully, again, it took us 5 years or more to get to 400 million rows, and our write throughput was much lesser than what MySQL was capable of replicating.
Got it.
So we would get like an internal gigabyte bandwidth or whatever meant like we were writing at like maximum 3 MB or 4 MB per second in some cases, and you would have 10 megabyte of bandwidth at a minimum to copy like this binary logs. And MySQL has multiple threads or stuff like that to be able to run these apply these binary logs, because if the log is for one table, it can be done via a separate thread. If it's in another table, it can be done by separate thread. So that way you could also control that in case if you want to.
Okay. Got it. Thanks.
Yeah, so I wanted to ask about proxy SQL and how you mentioned that it is like an Nginx load balancer for databases, but it allows you to connect through HTTP, how you would connect to a database. So is it like in this situation, is it like all like the application and the database are in the same network or something? Because previously when I've tried to do like layer 4 load balancing for databases on top of like through TCP, what I've faced is that the client or the application would need to pass an SNA in order for the load balancer to identify which host the request has to be routed to.
Perfect. Yeah, good question, right? So this is what I mean by protocol aware. if you use a HA proxy or even Nginx as a TCP load balancer on top of any other database, right? It doesn't speak SQL. Nginx doesn't speak SQL. HA proxy doesn't speak SQL. Proxy SQL speaks SQL. What does that mean? Like you have a MySQL : the host and the port and the username password kind of URL for the database, right? Proxy SQL gives you very similar URL. Like it will give you just a very URL which is very similar to that. It's MySQL protocol URL essentially. So from an application point of view, it thinks that it is talking to MySQL. It doesn't even know that it is talking to a proxy which is separate from MySQL. So it natively speaks the MySQL protocol. That means in your application, you will just have a single proxy SQL URL, and internally in your proxy SQL, you could route the traffic and whatever without any problem.
And is this,
Yeah, go ahead.
yeah, is this just for MySQL or like is it available for all SQL databases?
Yeah, so MySQL has proxy SQL. Postgres has something similar known as PG pool, which again does some sort of these things. It may not have a exact 100 to 100 feature parity with proxy SQL, but Postgres also doesn't have some of the problems that MySQL has in terms of schema migrations. Like schema migrations in Postgres are much more simpler, or they don't have this problem of replication lag and whatnot for most part, right? So PG pool is one for Postgres. I haven't come across for NoSQL databases. I'm not sure. We'll have to check. But these are the two: one for Postgres, which is PG pool, and proxy SQL for MySQL.
Yeah, thank you.
Hey, how does proxy SQL compare with RDS proxy? Have you evaluated that?
Yeah, interesting. Like I haven't, to be honest. Yeah, I don't know. I don't have a feature to feature comparison, but I'm guessing in terms of what they do internally, they might have their own, I guess, version or a proprietary way to do something. Like for example, I had gone into, like, there is another thing called keep alive D. If you are aware, keep alive D is for sort of high availability, in a sense that you have master and like you have two nodes, and keep alive D is in the you install keep alive D on both nodes, and it makes sure that if one of the node fails, other gets the IP address, so that from a client point of view nothing changes. So it's like almost like a virtual IP kind of feature. I'm guessing some of these tools, cloud specific tools, may be doing something like that to be able to have a similar feature set.
Okay, thanks.
Yeah.
All right. Thank you for all the questions. I see there's a lot of interest in that. So now we are going to take a break. Of course, like Chinmay and both of them are going to be available here for like your offline chats. So if you have more questions, please do ask. But we are going to take a break until 12:15. You can have a coffee, have side chats with like your fellow attendees here, and please come back at 12:15, and we will